a little bit here. We should have a minus, minus, and the minus because is a because a yeah is lacking to be faced. Okay, just modify this one, and here we should be have minus, and then you can get here is minus 31. Okay, yeah, but you know, actually we cannot operate the motors in this case. No, why? Because if the magnitude of EA are higher than the magnitude of V phase, okay, IA should be leading, not lagging, not lagging. Okay. So that means here to help us determine the boundary of Bmax and Qmax. Okay, yeah. So if this one now become the generator, it will be okay. So now synchronous motor modified to become synchronous generator. So here we have V phase, okay, and then here we can get the EA, yeah, and the phase angle here 90 degree. That means EA is 419.23 with a plus 90 degree. Okay, it will be so that means the synchronous motors becomes synchronous generator. So for synchronous generators we have the formula, right? We have EA E V phase plus JXSIA. We assume is RA is 0, right? Yeah. This also okay. Why? Because the magnitude of AAE 419.23 volt, and the magnitude of V phase now is 254 volt. Okay. Yeah. So the synchronous motor now operate as a synchronous generator motor. Okay. Yeah. So now we can calculate IA. So IA now becomes EA minus V phase divided by JXS, and EAE 419 with 90 degree minus V phase is 254 with 0 degree, then over JXS. JXS mean 1.5. 1.5. So you get how many? 90 degree minus 154 with 0 degree divided by 1.5 I. Okay. So we get 326.6 with also 31.2 ampere, right? Okay. So for this case, now this is IA. This one the IA with the phase angle 236.6 with the phase angle 31.2 degree. Okay. Yes. Okay. So here is JXSIA. Okay. This is of course perpendicular. Okay. Yeah. So now in this case, actually in this case mean we operate the machine as a synchronous generator. Okay, generator, and Qmax also the same, the 127. 127 kvar. Okay, yeah. So this is the meaning of of uh, of this case. You know, actually, if IA here, V phase here, and the IA should be leading. But this is lagging. So we think about synchronous motors now operate as a generation mode. Okay, so now this is IA, and then we have this is 31.2 degree. Okay, so this one is leading, and this is leading. Yeah. So um, this one is EA, yeah, and this one is V phase. Okay, yeah. That's all. So now remember that we have homework. Okay, from problem 1, 2, 3, 4, 5, blah blah blah, and you should resubmit. Sorry, you should submit um, the homework. Okay. Yeah. So here, yeah, we have the homework of lecture 3. So now come to lecture 4. Lecture 4, part 1. Yeah. Okay, so now we finished the studying synchronous machine. So now we move to synchronous. We move to induction machine, or we say a synchronous machine. Okay. Yeah, of course, for the machine, we have a generator and motor. But we skip a synchronous generator, which we only study synchronous motors. Okay, sometimes we say asynchronous motors, sometimes we say induction motors, the same, asynchronous motors. Okay, and we also have one lab session about these lectures, induction motors. Okay, so of the objectives of these lectures, you can understand the key difference between synchronous motors and induction motors. Okay, synchronous motor we study before, right? Now we have IM mean induction motors. We have rotor slip and rotor frequency, how to analyze the equivalent circuit of induction motors, understand the power flows, power flow diagrams, yeah, torque speed curve. Okay, torque speed curve of induction motor, right? Yeah. So the key difference between synchronous motors and induction motor is the rotor winding. Okay, so you should remember for synchronous motors, this is stator, right? And this is rotor. So at the rotor, we have rotor winding, or we say field winding, and then we connect what? We connect a DC, a VDC, and this one is IF, right? Yeah, this is synchronous motors. But for induction motors, okay, we don't use DC power supply. Okay, so if we don't use if we don't use DC power supply, how can we get the rotor current? Okay, right? For synchronous motors, we supply the DC voltage. Okay, so this one become the closed circuit, so we get the rotor current or field current. But for induction machine, induction motor, we don't have DC power supply, so we need to think another way to generate the rotor current. Okay, so later on I will show you. Yeah, and we also understand how to start induction motors, how to control the speed, how to measure parameters of synchronous motor or induction motor. Yeah, and also understand the motor ratings. Okay, so that means we have some rated parameters of induction motors. Okay, so here you can see this is the configuration of induction motors or asynchronous. Vietnamese meaning is động cơ không đồng bộ, asynchronous. Okay, yeah, but normally we just say induction motor. Okay, yeah. Now we go to the session 4.1. We discuss about construction of induction motors. Yeah, as mentioned before, we have two different types of induction motors. Yeah. So the key difference between synchronous motor and the induction motor is rotor side. Okay, so for induction motors we have two kind of rotors. The first one is cage rotor and the second one is wood rotor. Okay, so this one is cage rotor, this one is wood rotor. Yeah, for wood rotor we have rotor winding, right? We have rotor winding. Here is rotor winding, right? But for cage rotors we don't have winding, but we have bar. Okay, we have many bar. Okay, yeah, Vietnamese thanh dẫn. Okay, we have many rotor bars, but for wood rotor we have rotor winding. Okay, and you can see we don't have DC power supply. So if we would like to get the rotor current, we need to make the short circuit. Okay, we need to make a short circuit of the rotor winding. So how can we make short circuit? Here, see, you can see this one and this one. This is a shock ring. We say shock rings, vòng ngắn mặt. Okay, shock ring. Yeah. So if we have a rotor bar and we have two shock rings, this one becomes the closed circuit and we can get rotor current IR. And here, you know, this is wood rotor, so we need to make short circuit here. Okay, and we also get the IR. Yes. Why? Because if we know IR, because if we know IR, we can generate BR. This is rotor magnetic field. Okay, yeah. So now, this is these cage rotors. You know, we have two shock ring, the first one and the second one here, shock ring, and we have rotor bar. Okay, yeah, look, the cage rotor consists of a series of conducting bars, yeah, laid into slots. Okay, cave in the face of the rotor, shorted, and either end by shock rings. Yeah, this is shorting rings. Okay, yeah. So now this becomes the closed circuit at the rotor side, so they can generate IR, a rotor current. Okay, so now look at this one. This is this is a conduction bar. You know, this is conduction bar. conduction bar. Yeah, and we have this is shock rings. Yeah, so we can get this the rotor current. Okay, now we have wool rotor. So this is the winding. So how many rotor winding? Okay, yeah, 3. Why? Because we have 3-phase induction motors. Okay, so 3-phase, we have 3 windings, and of course, one winding has many coils, and one coil has many turns. Okay, so how can we make the closed circuit at the rotor side? We should use slip rings. The slip ring, because we have 3 windings, so we have 3 slip rings. Slip ring for phase A, slip ring for phase B, slip ring for phase C, and this one is process. Process mean the Vietnamese chổi than. Slip rings Vietnamese the cổ góp. Okay, so now we have 3 windings at the rotor, phase A, phase B, phase C, and we connect to the process. Okay, and then at the process, okay, we can make the short circuit here. This is phase A, this is phase B, this is phase C. So normally we connect the rotor winding with external resistor. Okay, so we make this one. So that means we have short circuit at the rotor side. So we can generate IR. Okay, yeah. So anyway, we have 2 ways. So if we use cage rotors or squirrel cage rotors, we need the conduction bar and shock rings. Okay, so if we use a wool rotor, okay, we have rotor winding, and we should use 3 slip rings and 3 brushes. After that, we can make the closed circuit and we can generate rotor current. Okay, yeah. Any questions? Yeah, so this is the key difference between the construction of synchronous motor and induction motors. Thầy Bá, any questions? Long, any question? Long? Okay. So next. Now we go to this second session, 4.2. We have some concept in relation to the induction motors. Okay, yeah. Now we come back a little bit. So if we have synchronous generator or synchronous motors, okay, we have the synchronous speed. This is 60 FSE over B. Okay, right? And for synchronous generators or synchronous motors, at the rotor side, we have a DC current. Okay, yeah. So at the stator side, we have rotating magnetic field. Okay, so we can make sure the speed of stator stator magnetic field and the speed of the rotor, they have the same speed. We say synchronous speed, but for induction motor, at the stator induction motor, at the stator we have rotating magnetic field. Okay, rotating stator magnetic field, and at the rotor we also have the rotating rotor magnetic field. Okay, why? Because because at the rotor, because at the rotor, this is three phase, right? This is three phase rotor winding. Yeah. So if we have three phase rotor winding, they automatically generate the rotating magnetic field. Okay. So now, yeah, for induction motors, we have rotating stator magnetic field. We have rotating rotor magnetic field. So we cannot make sure the speed of the stator, okay, uh, uh, is equal to the speed of the rotor. No, they are different because we have rotating stator magnetic field, we have rotating rotor magnetic field. So now the rotor speed will be different from the synchronous speed. Okay, yeah, okay. So here you can see, yeah, you can see this is the stator magnetic field, right? Stator rotating magnetic field PS. Okay, so if stator magnetic field goes across the rotor winding, okay, we can get induced voltage, right? Yeah, we can guess the induced voltage ER, and for the rotor windings, okay, we have more reaction, more reactance. So IR lags ER. Okay, so this is ER, so this is IR. Okay, so now we have IR, we can generate BR. Okay, and BR is lagging to IR 90 degree. Always. So now we have BS. Now we have BR, so we can get B net, right? We can get a B net. Okay. So this is BR, this is BR, and this is BS. Okay. So here you can get a B net, right? B net. Yeah. B net. And we can calculate the induced torque EK BR cross BS. Okay. Yeah. 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 We also have more description here, so you read it for yourself. Okay. Yeah. Now look. 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 So we have some concepts. Okay. So for induction motors, we have the first concept. This one is synchronous, right? Synchronous speed. Okay, synchronous speed, or we say stator frequency. Stator frequency. Okay, so we have synchronous speed. Okay, or the stator frequency, or the stator speed of the speed of stator. Yeah, the speed of stator magnetic field. Okay, so we say N sin. So N sin is 60 FSA over B. Of course, we know FSA mean stator electrical frequency, right? Yeah. So we have rotor speed. Okay. We have rotor speed of the induction motors. Okay. And of course, the rotor speed will different from synchronous speed. Okay. So the difference between synchronous speed and rotor speed is slip speed. Okay, so sometimes we say n rotor, sometimes we say nm. Okay, the same, this is the rotor speed of induction motors. Okay, or we can say the rotor shaft speed. Okay, yeah. So now we have uh, the difference between synchronous speed and rotor speed is slip speed. So slip means the tốc độ trường. Okay, so slip speed is n sin minus n rotor. Okay. Yes. Okay. Okay. So then, uh, so if we make the ratio of n slip over n sin, we can guess S. We can guess S. Time 100%, you can guess S. Okay. Yes. So if you time 100%, the unit is percent. Otherwise, if we say S is n slip over n sin, that's okay, So n slip is what? N slip is n sin minus n rotor. So divided by n sin. So that means n sin, you get 1 minus what? Minus n rotor over n sin, right? And this is slip. This is slip. Or you can say n rotor e 1 minus s time n sin, right? Yeah, we modify a little bit, This is we move this one to the left side and add to the right side, so you get n rotors is 1 minus s time n sin. Okay. Yes. Yeah. Here n m or n rotor is 1 minus s time n sin. Okay. So now summary. Now we'll make summary. So when we talk about speed, when we talk about speed, well, how many kinds of speed we have? 3. We have synchronous speed. This is n sin. Okay. We have rotor or shaft speed. We say n m or n r or n rotor. Okay. Rotor. So we have slip speed. This is n slip. N slip is the difference between n sin minus n r. Sometimes we use nm, sometimes we use nr, sometimes we use n rotors. That's okay. We have the same meaning. Yeah. Why we have the slip here? Because n sin different n r. Okay. So actually we have n slip. Okay. Yeah. So now we have the formulas. Yeah. So we define slip. Slip is S, and S is n slip over n sin. Okay, equal to 1 minus n rotor over n sin, right? And we modify a little bit, you get n rotor is 1 minus s times n sin. Okay, yeah. So this equation is similar. This is rotor speed and the unit is RPM. So if we modify RPM to become omega, it is radian per second. Okay, we have the same. So now we have omega rotors is 1 minus f times omega sin. Okay, yeah. So we have the equivalent formula here and here. Okay, it's up to use. So if we use radian per second, I mean angular speed, we use this formula. So if we use RPM, we use this formula. Okay. Yeah. Okay. Yeah. Let me see. Okay. Too far. Okay. Yes. So welcome back. Yeah. Now we talk about these electrical frequencies. Electrical frequency. So the question is, what will the rotor frequency be for any arbitrary rate of the rotor rotation? So what does this mean? That means for the stator, we have winding, right? We have winding phase A, phase B, and phase C. So for the rotors, we also have phase A, phase B, and phase C. Okay, so at the stator, we have FSE, SE is stator frequency, right? At the rotor, yeah, we have FRE, that means the rotor frequency. Why? Because we have IS, we have stator current, so we have FSA. So here, at the rotor we have IR, so we have rotor frequency. Yeah. So actually, this is stator electrical frequency, and this one is rotor electrical frequency. RE means RESE. Okay. Yeah. So the induction motor work by inducing the voltage and the current in the rotor of the machine. Okay, for that reason, it has sometimes been called the rotating transformer. Okay, so for the transformers, okay, we have two winding, right? We have primary winding and secondary winding. Okay, this is stationary. This is stationary. Okay, in this one we connect to the power supply, and this one we connect to the load V2. Okay, and the magnetic core is stationary. But now look at this one. This one is stator, and this one is rotor. Okay, and the rotor rotate, right? Okay, so when at the beginning the rotor is stationary, and then if we supply the current, the rotor will rotate. So this is the reason we say here is rotating a transformer. Okay, yeah. So if the rotor is locked, okay, so if the rotor is locked, okay, so induction motors becomes transformer, right? Because if the rotor is fixed, the rotor is locked, that means we have no rotation. Okay, so induction motors becomes transformer. Okay, so the rotors is stationary, mean NR is 0, right? Because the rotor doesn't rotate, so NR is 0. NR is 0, that means S is 1. Why? Because SE and NR is 1 minus S times NC. Okay, so if the rotors doesn't rotate, that means NR is 0. NR is 0 if S is 1, right? S is 1. So if the rotor rotates, IM now becomes rotating transformer and H different 1. Okay, why? Because we have NR different 0, NR different 0 because the rotor is rotating. Okay, so NR is different from 0, NR is different from 0 mean H different 1. Okay, yeah. So here, look, if the rotor turns at the synchronous speed, okay, so now if NR becomes NSyn, if NR become NSyn, that means S is 0, right? NR become NSyn, this means S is 0. So S is 0, we have NR equal to NSyn. But we cannot get the condition that the rotor turns at the synchronous speed. No. Okay, so we just have two cases. IM induction motor operate as transformers. This means NR is 0 and S is 1. So if we have the rotation of the rotor, so IM becomes rotating transformers and NR different 0 and S different 1. From 1. Any questions so far? Hey, Ba, any questions? Okay, so we summarize here, you know. So S is 1. S is 1, that means the rotor is locked, right? Is locked or stationary. Yes, yes. So we know NR is 1 minus S times N6, you know. So S is 1, that means NR is 0. Okay, so NR and M is 0. Yeah. So this one becomes the transformer, transformers. So for transformers, you know, we have the same frequencies between the primary side and the secondary side. Okay, yeah, yeah. If we come back to the theory of the transformers, we have the frequency at the primary side will be equal to the frequency of the secondary side. So here we say FSE, and for the rotor we have FRE. You know, so if induction motor becomes the transformers, okay, so now FREs become FSAs because we follow transformer theory, right? Okay, so now S is 0, S is 0, S is 0, that means the rotor equal to the rotor speed equal to synchronous speed. Look, the rotor speed equal to synchronous speed. Okay, so we have the rotor frequency is 0. Why we get this one? Why we get this one? I will demonstrate to you and later. Now we just accept the formula first. So we have FRE is S times FSA. Okay, FRE is S times FSA. Okay, yeah, very important formulas. Yeah. So for now, S is 0. S is 0. So if we apply these formulas, you can get FRE is 0 times SA equal to 0. Okay, yeah, yeah. So how can we get this formula? This one we come to next slide. You can see that the Okay, I will demonstrate to you how can we get this one, you know. So we have n since is equivalent to FSA, right? Why? Because n since is 60 FSA over B. Okay, yeah. So n since is equivalent to FSA. So n r, okay, equal to FR, and n slip is equivalent to FRE. Why? Why? Because if we have slip, that means we have rotor current. So if we have rotor current, you can get FRE. Okay. So anyway, the synchronous speed is equivalent to stator electrical frequency. The slip speed is equivalent to rotor electrical frequencies. Okay. So what does it mean? FR, you know? So FR mean rotor mechanical frequencies. Frequency. That means the rotor's frequency, you know, mechanical frequency. This is a rotor electrical frequency. Okay. So yeah. So and we have n slip. E is what? E 1 minus S. Sorry. Sorry. Okay, we have NR. NR is 1 minus S time N slip. N synchronous. N synchronous, right? N synchronous. Okay. So that means we have N sin minus S N sin, right? Minus S N sin. Okay. Yes. So S time N sin is S slip. N slip. N slip. Okay. Or we can say N slip ES time N sin, and N sin E equivalent to FSE, and N slip equivalent to FRE. FRE. So we have these formulas. Okay. Yeah. So we have FR. So we have N rotors is 1 minus S times N sin, and NR is equivalent to FR. Okay. So 1 minus S. So N sin is equivalent to FSE. FSE. So we have these formulas. You know, when we calculate rotor electrical frequency, this is S times FSE. When we calculate rotor mechanical frequency, okay, so FI is 1 minus S times FSE. Okay, yes. Yeah. And of course, we have some formulas here, but it's easy for you to understand. So the key point is here. Okay, now we make the summary. Come back here. Now we talk about frequency, right? Frequencies. So we have 3 different frequency. We have FSE, FRE, and FR. You know? Yeah, of course we know what are they. Okay, so I just skip. So we have FRE, ESFSE, and we have FR is 1 minus S times FSA. Okay, and FSA is what? N sin is 60 FSA over 4 pairs. So this is N sin times 4 pairs divided by 60. Okay, so if we know FSE, we know S, we can calculate We know FSE, we know S, we can calculate FRE and FR. Okay. So continue. Yeah. So we know NRE and since we have N sleep, right? N sleep. E and sin minus NR, right? So that means N sin E and sleep plus NR, right? Here, here, yes. And N since is equivalent to FSE, and R equivalent and sleep equivalent to FRE, and NR is equivalent to FR. So now look, we have very important formulas. You know, FSE is the summation of FRE and FR. Okay? Yes. Yes. Any questions? Any questions? Anh Khoa, Phương Anh, Đỗ Phương Anh. Any questions?
Dạ không.
Okay, so here, okay, so I emphasize to use this one is rotor electrical frequency, and here is stator electrical frequency. And what's the S? Yeah, we know SE, sleep. Okay, so example. So for this example, they give us IM, induction motors, okay, and look the frequency. So they give us FSE is 60 Hertz, right? We have 4 poles, so that means pole A2, we have this is 3-phase, so we have VL, E, 208 volt, and HP. This is motor, right? So we have B out, E, B rated, E, mechanical, right? Mechanical, and this one is 10 HP. Yeah, and they give us the sleep, right? S. So SE 5%, 5% means 0.05. Okay, so they require us to calculate the synchronous speed. Okay, synchronous speed mean N sin, right? N sin is 60 FSE over B. That means 60 times 60 over B, BE2. Okay, so you get 1,800 RPM. Okay, so rotor speed. Rotor speed mean rotor mechanical speed. That means NR. So NR is 1 minus F times N sin. That means you get 1 minus 0.05 times N sin here, 1,900. So you get how many? You get 1710 RPM. So now look, we would like to calculate rotor electrical frequency. That means FSE. FSE is F times, sorry, right? Sorry. This is This one is FRE, FSE. So SE 0.05. With time with FS it is stator electrical frequency 60. So you get 3 hertz. 3 hertz. So after that you can get FR. FR is 1 minus S times FSE, or you get the 57 hertz. 57 hertz, right? Look, what's the shaft torque of this motor? That means they require to calculate output torque. Okay, output torque, very easy. And this is the answer, right? That is the answers. And output torque mean load torque equal to output power over omega m. Omega m means mechanical angular speed, or you can get B out of omega r, the same, and B out is 10 HP, and LHP has 746 watt, so 746 watt divided by omega r, so omega r is 2 by NR over 60, right? So you get how many? You get 2 by NR here, NR, so 1710 over 60. Yeah, so you get how many? 41.7 Newton meter. So what is it? What is it? So what is it? So this is the output torque, okay, of induction motor. Why? Because for the motor, this is the induction motor. This is the motor. Yeah. So the shaft of the motor will connect to the load. Okay. Yeah. Maybe here we have some bearing and yeah, blah blah blah. Okay. Anyway, so this is induction motor. So the shaft of induction motors, yeah, will connect to the mechanical load. Yeah, mechanical. Here, yeah. It is mechanical load. Okay, or mechanical load systems. Okay, so this is the rotors of induction motors. Any questions? Thấy bà. Okay. Yeah, next. Okay, next. So we have the video of the operation of induction motors. So now, yeah, look at. Yeah, this is stator. This is a squirrel cage rotor. Yeah. Yeah. This is stator winding. Okay. This is yeah. This is piece of K rotors we discussed before. Okay. Yeah. Yeah. Okay. So we we supply the power, AC power into induction motors, and we can get the rotating stator magnetic field. So if the stator magnetic field rotates, so the rotors is also rotate. Okay, so here with the other one, this is a stator magnetic core. Okay, this is a stator winding. Yeah, so if we have the current into the stator winding, we can get, we can get rotating stator magnetic field, right? Yeah. The three-phase windings. Yeah. Because we have three-phase windings, a three-phase current, so the stator magnetic field is rotating. Yeah, rotating. Yeah. We have three-phase stator current, so we get stator rotating magnetic field. Okay. Yes. This is zero case rotors. Yeah. So because we have the conduction bar, we have the soft ring, so we can get the induced voltage. Okay, and generate rotor current. After that, we can get the rotor rotating magnetic field. Okay. Yeah. Yes. Okay. And now we go to the session 4.3. We discuss about equivalent circuits. Equivalent circuits of induction motors. Yeah. We should have the general ideas first. Okay, so we have the outer ring. For the outer ring, this is stator, and for inner ring. So for inner ring, this is the rotor. Okay, so for the stator windings, we have stator resistance, stator reactance. Okay, we have stator current and V1. Okay, this is phase. This is phase parameter. This is magnetic circuit. Okay, this is reluctance. This is reactance, magnetization reactance. And for the rotor, we have rotor resistance, rotor reactance, slip, right? Slip, and rotor induced voltage. Okay. Yeah. So so we separate. Why? Because this is stator, this is rotor, so we have the air gap. We have the air gap. This is the air gap. Okay. So if we would like to combine, you would like to combine stator and rotors. Yeah, we need to modify a little bit. We need to refer on rotor parameter back to the stator, similar to the transformer. For the transformers, if we would like to get equivalent circuit, we need to refer on secondary parameters, okay, back to the primary side. Okay, so now similarly, this is rotor. We have rotor current, rotor resistance, rotor reactance. Right? So we need to refer on rotor parameter back to stator. Okay, so if we so I2 refer back to stator, you get I2 over comma I2 R2 over comma blah blah blah. Okay, so we can get only one circuit. Now we already combine a stator and rotor together, okay, into one circuit. So this is the idea, right? This is the idea. Yeah, sure. Coming from the ideas, okay, we need to develop the equivalent circuit for induction motors. Now, we have some parameters you need to remember. Okay, now come to here. Okay, for so for every induction motor, right, we have stator and we have rotor, right? Yeah. So if we have resistance, normally for stator we use a strip 1 or S. For rotor we use a strip 2 or R. For example, we have R1 or RS. This is stator current, right? This is stator resistance. We have X1 or XS. So normally we use what? R1 is a stator resistance, X1 is stator reactance. We have I1. I1 is what? A phase current at the stator. Right? Okay, we have a V1, or sometimes we say V phase or V phase. What is it? This is phase voltage of induction motors. Input of phase voltage. We have which one? We have B1. This is B1 3-phase. This is stator power or input power. Okay, yeah. So for the rotors, we have a subscript 2 or R. So normally we use R. Okay, so we have RR, rotor resistor. We have XR, rotor reactance. We have IR, rotor current. We have slip. We have VR, or normally we do ER. Rotor induced voltage. Yeah. Now we have what else? Or sometimes we use R2, X2, I2, E2. Okay, yes. Then we have a magnetic circuit. Okay. Magnetic circuit. We have RC, this is reluctance. We have SM. This is magnetizing reactance. Okay, we have I0 mean magnetizing current. Okay, yes. So this is the list of important parameters for stator winding. Okay, rotor winding and magnetic circuit. Okay, so come back. So here you can see, we have I1 stator current. This is per phase. This is per phase. Okay, per phase equivalent circuit. So we have 3-phase induction motor. So we have 3 equivalent circuits for phase A, phase B, phase respectively. So this is stator resistance, stator reactance, phase voltage input, you know, this is input phase voltage, okay, IM or I0, okay, reluctance, magnetizing reactance, okay. So here, this is air gap, this is air gap, you know, air gap. So this one is stator, this one is rotor. For rotor, we have rotor current, rotor reactance, rotor resistance, and induced voltage. Okay, so this one is rotor induced voltage. Okay, yeah, and I2 is not here, you know. I2 should be here. Should be here. IR or I2. Okay, so anyway, here we have the air gap. Okay, so if we would like to combine, if you would like to combine stator and rotor together, we need to make sure E1 equal to ER, you know. So if we have the same voltage between this terminal and this terminal, we can combine the stator and rotor circuit. But actually, E1 is different ER, you know. If the rotors is locked, if the rotor is locked or the rotor is stationary, E1 is R. Yes, because it's like transformer. And we have the same turns. That means NS equal to NR. Okay, NS equal to NR, and then rotor is locked. You get E1 and ER. You can combine together. But if the rotor is rotating, okay, so that means E1 different ER. So we need to refer ER back to stator. We say ER overcomer. Okay, so ER overcomer will equal to E1, and then we can combine the stator and rotor circuit. So we need to refer ER, IR, XR, RR back to the stator. Okay, yeah, so after that you can combine stator and rotor circuit. Okay, this is the ideas. So yeah, this one for your reference, so we skip it. Now look, now we know the idea, right? We know the idea. So we have two cases. Yeah, we have two cases. I just pick up rotor circuit. So this one is ER, right? ER, and this one is RR. This one is JXR. Like this. Yes, like this. Okay. Yeah. So if we have a locked rotor condition, locked rotor condition means the rotors is locked, right? The rotor is locked. That means S is 1 and NR is 0. Okay, so we say now we say ER become ER0, SR becomes SR0, and RR becomes RR0. Okay, 0 mean for the condition of locked rotor. Okay, so if the rotor rotates, if the rotor rotates S different from 1, okay, of course we know S is higher than or equal to 0 and less than or equal to 1. Rotate, sorry. So if rotate, that means S is not equal 1, okay, just less than 1. Okay, yeah, so S S, if this is the condition of S or S different from 1. So now we have ER is S times EI0. Okay, and XR equal to S times XI0, and RR is RR, you know, because it is resistant. Okay, this is in the dependent of S. Okay, yeah. Okay, so for this E, the idea is for two condition of rotor. Okay, yeah. So if the rotor, yeah, so here, look. So if S is 1, you know, so you get the 1, you know, so you get 1 times EI0 equal to ER0. Okay, yeah. And if S is 1, RE is FSE. Okay, so we have XR. Why we have this one? Why we have XR is S times XI0? Because if the rotors is locked, okay, XR is omega RE. No, XR is always omega RE times LR. No, omega RE mean the rotor electrical angular frequency, and omega RE is E2 by FRE times LR. Okay, and we know FRE is S times FSE. Okay, yeah. So if we take S outside, inside we have 2 by FE I0. Okay, so 2 by FSE LR mean XI0. That means XI0 is omega SE times LR. Okay, yeah. Any questions? Thầy Ba, any questions? So now with summary. Okay, come back here. You know, if the rotor is locked or stationary, you know, we get ER is EI0, and XR is XI0, and RR is RI0. Okay, so because the rotor is locked, so this one like I am like transformer. Okay, transformer. So we have FSE equal to FRE, right? Because this is transformer. Okay, so now, okay, we have this rotor, so we have omega SE, sorry, omega RE, omega RE times LR. Okay, but because FSE equal to FRE, so mean FSE equal omega SE is equal to omega RE. So here you get omega SE, right? Omega SE times LR, and omega SE mean 2 by FSE LR. Okay, so this one is XI0, and you know this resistance is constant independent of the frequency. Okay, this is case 1. So K2, the rotors is rotating. So if rotor is rotating, we have FRE different FSE in such a way that FRE is ES times FSE. Do you remember these formulas? Yes. Okay. So continue. So now we have ER, you know, ER now become S times ER0 because we have S. Okay, we have SRES times XI0 and RRE also RR0. Okay, so why we have S here? Why we have S? Because SR become omega RE times LR. So now omega RE is S times omega SE. So this is S. Okay, omega SE. Right? Omega SE. So now you get S omega SE LR and S or you get S 2 by FSE LR. So 2 by FSE LRE XI0. So you get S XI0. Okay, and similarly you can get ER ES EI0 and SI is SXR0. Okay, yeah, yeah. Okay, so now now look, okay. So now look at this one. So now for this is the general case. We don't care about the rotors is locked or the rotor is rotated because we know if we have locked rotor, S is 1. And if we have rotating, yeah, S different one. Okay, so here this is the general. ER is S times EI0 and XR is S times XI0. This is RR. Okay, so we apply Kirchhoff 2 for this one. Okay, so if we apply Kirchhoff 2 for this one, we get what? If we apply Kirchhoff 2, we have ER E S EI0, okay, E RR plus J XR times IR. Okay, and we know RR and XRE J XI0 S, right, time IR. Okay, yeah, so here you can get IR. So IRER over what? Over RR plus JXR here. Okay, and ERE EI0 and RR is RR and XRE X times XI0. Okay, so if we okay, continue here, we just modify a little bit. So ER mean SEI0, right? And here RR plus JXXI0. So if we divide this by S for numerators and divide this by S for denominators, so now you get RR over S. It's not S here, so now you get this one. Okay, so now we have IR become ER0 over RR over S plus JXI0. Why? Because here we have S, here we have S. So we delete S, we divide it by S. So we have ER0 over RR over S plus JXI0. Okay, it's here. So this one we say is equivalent rotor impedance. Yeah, so now, so come on this one mean ER0E RR over S, right? Plus JXI0 times IR. Okay, so now at beginning we have this one, right? ERES EI0, this one and this one, and we modify, you get this equation. For this equation now, this one is ER0, this one is RR over S, right? And this one is ER0. So we can modify from this rotor circuit to become this one. Okay, why we need this one? Because for this one we can fix EI0, right? EI0, yeah, and EI0 for the transformers, right? So EI0 now This is constant. This is constant. Okay. Yeah. So if we we stop now. Slide 30. Okay. Yeah. So summary. Before we stop. Okay. Summary. Yeah. Summary. Okay. Sure. Yes. So at the beginning, we have here ER. Okay, and this one is JXR. This is RR. Right. This is rotor circuit. Right. Rotor circuit. Okay. Yeah, and we know ER is times EI0, right? Yeah. Yeah. So, and then we know JXI means JXXI0 is ERR. Okay, become this one. Okay. So, if we delete this, delete S here, delete S here, so we should divide this by S here. This one is also IR. This one is IR. Okay, so now this one becomes ER0, right? ER0. Now you get JXI0, right? And now, okay, we get RR over S. Okay, yeah. Yeah. So at the beginning, now ER is variable. Why? Because ER is the function of S times EI0. But when we modify now, the voltage here is constant. XI0 is constant. Just here is variable. Variable. Why? Because R over S, right? So that this is variable. This is constant. This one is constant, right? Why is variable? Because if the rotors is locked, that means S is 1, so we have RR over S is RR. Okay, so if the rotors is rotating, okay, that means S is higher than or equal to 0 and that's 1. So we have different RR over S. Okay, so if S is 0, you get RR over S is approach to infinite. Okay, approach to infinite. So if S is higher than 0 and less than 1, we have RR over S. This is some certain value. But we can know RR, RR over S should be higher than RR because S less than 1. Okay, S is less than 1, so RR over S is higher than RR. Okay, so we have three cases, right? Here, here, S is 1. So you get RR, so S is infinite. S is 0, so RR over S is infinite. So, and then if S is higher than 0 and less than 1, you get RR over S is higher than RR. Okay, so this is the summary. Any questions? So now we stop at this slide 30, and see you next week. Yeah, we hope we can finish lecture 4, part 1, part 2, and part 3. Okay. Yeah. Any questions? So if you have no questions, we stop now and see you next week.